And the words that are similarly clustered together, in this case, we talk about SeaWorld, dolphin, and purpose, we expect them to be relatively closer in this latent space. And then words that are somewhat unrelated, like Paris and camera, are going to be somewhat further away. And when I say latent space, if we have a sequence of numbers, you can think of them as coordinates as well, right? Here we represent them in a 3D space, but in reality, most embeddings are anywhere from 100 to a few thousand, quote unquote, dimensions. But again, this is just a representation here. The idea is to give you a visual example, but don't think of this as literal. So in the example that I'm using here, the classical example of word embeddings come from a model called Word2Vec, and this was released by Google in 2013. And the idea is that we represent each word with a vector of a relatively small sequence of numbers. The main thing that is very interesting about Word2Vec is that the similarly words that are similar in the semantic sense are also similar in the latent space sense, as in they are actually physically together when you compute the distance between those two vectors. Further, you can represent different words by mathematical operations of others. So you can expect, and this is roughly speaking, it's not exact, but if you subtract the vector man from king and you add the vector corresponding to woman, you get something closer to whatever queen should be in the latent space. Again, this is not exact, but you get the rough idea. And the idea is that we do this in a semi-supervised way using some neural network. To illustrate the point that I meant about similarity and directionality is that the direction and distance between king and queen is roughly equivalent to the one between man and woman. And again, this is just a visual example. In the 3D space, we're talking about an n-dimensional space in real terms. But you see the same relationship between not just nouns, but also other kinds of relationships, such as from walking to walked, from the ongoing tense to the past tense, or even from countries to the respective capitals. Now, the more that you try to push the limit, the more that those relationships break down. And that's just visually expressed here, that you don't see a very clear relationship and a very clear direction between the countries and the capital cities. That's more like what you will see in the real world. So how do we use latent space in AI? Well, first, it is a very convenient way to do dimensionality reduction. In many cases, some of the media is extremely rich. Think, for instance, images that are composed of thousands, if not millions of pixels. And we can reduce all that into just a very small sequence of numbers that actually carries quite a pretty good amount of meaning, enough to be able to do some learning on the reduced representation as opposed to the original media. We can also use it for feature extraction. Again, that's in part because it is such a reduced representation. We can simply look at specific components of it. And then finally, it is pretty heavily used when it comes to generative modeling, especially in the text-to-image model space. We'll cover that specific use case in depth later. So that's latent space. We can probably save all the questions at the end, but if you have any questions about latent space, I suggest you write it down because we are going to cover a whole bunch of things before we get to the Q&A part. Now let's move on to foundation models. And I want to explain what foundation models are, just from a very high-level overview before we dive into how to measure some biases, just to make sure that we're on the same page and that what I understand as foundation models from the perspective of my research is laid on the table here. So for the purpose of my research, the foundation models are what they are based on two core attributes. Number one, they are large in scale. They use a very large quantity of data, and they have to be trained with minimal supervision, in part because they have such amount of data. It will be very difficult to get some strongly labeled data at the scale that it is needed to have a proper foundation model. The second core attribute is that they are general purpose, and that is A foundation model is an AI model that can do more than just a single task. And then because of that, it is being used as a foundation for other task-specific models. And there comes the term foundation models. To give you a counterexample, way back when we had intelligent systems that were very good at, say, playing chess. It doesn't mean that they are not intelligent systems. It just means that they are very narrow purpose. So for that reason, those are not foundation models. So let's go through an actual example. Let's think about large language models, LLMs. So they have been trained using a very large corpus of text. They're going to predict the next word given the n previous words. And they are capable of doing a number of things such as computing embeddings, summarizing, and generating text. And then finally, they can be fine-tuned to provide some purpose-specific or to tackle some purpose-specific tasks, typically in the text-related model space. Well, based on our previous criteria, we've actually met both of the two core points and then the two sub-points for each of the qualities that describe a foundation model. We use a very large quantity of data, and when we predict the word given the n previous words, that means that we have actually minimal supervision. We're able to do more than just a single thing. It's actually a variety of tasks, and then they have been used as a foundation for many other models. So here we have it. We tick all the boxes as far as we are concerned for the context of this talk. This is a foundation model. But how do we get here? So I talked about some of the chess playing AI, if you want to call them that way, models before. So before we had what we today consider as AI, we were in what I describe as the dark ages. This is when you had to build your own ML infrastructure, anywhere from the training code to the inference code to how do you do the sampling. Everything had to be completely bespoke. And typically there was very little sharing from one lab to the other, because when you build the entire pipeline, you do it specifically for whatever research or whatever task you have at hand. And that was fine and all, but at least in the world of software, we always benefit from sharing, and especially in the open source side of things. So then came the ML frameworks. These are robust, battle-tested machine learning frameworks. And the core example, one of the first that came out, was TensorFlow. And the idea is that now, if you were doing machine learning research, you could focus on the interesting part of your research, the part that was novel. This time, it was typically the neural network architecture, right? And you didn't have to worry about writing the training loops or writing the inference code or even on the deployment side of things. All of that was taken care of by the machine learning frameworks, and that was a massive leap forward towards foundation models. Then we entered the era of the bigger is better in the machine learning world, and we were getting better and better results the bigger the models got. The main issue here is that that takes up a lot of resources and a lot of time that it takes to train these models. If you are somebody like Google, that's not typically a problem, but if you are a relatively small lab trying to do machine learning research, that becomes increasingly difficult. So then we discovered a trick called transfer learning. The idea is that you could take some of these big models that were trained by somebody that had more time, money, and resources than you did, or at least were willing to spend more than you did, and you could take that model basically as is, then take whatever data you had, which required approximately an order of magnitude less, if not even less data than the original model required to train. And then you literally retrain the model with your data by simply updating the weights ever so slightly. And there's different techniques. You could update all the weights or only a few layers. That was a whole other topic of research. And the idea is that you were actually getting state-of-the-art results by spending, again, 1/10 or even less of the resources required to train a model from scratch. And that worked great for quite a while. But then models got even bigger. And what we consider today as small models were actually some of the biggest models that we had during the transfer learning era. So now we've entered a new era. And I guess I forgot to update the slides. So here we have ZSL and FSL. That stands for zero-shot learning and few-shot learning. And the part that I forgot to mention here is that we also have the parameter-efficient fine-tuning. Parameter-efficient fine-tuning is the next iteration of transfer learning, where we actually have gotten very, very good at being able to fine-tune models in a way that requires even less resources. Um, it is actually a very interesting topic of research. If you want to learn more about it, the main concept being used here is a paper from Microsoft, and the term you want to search for is called LoRa, L-O-R-A. In any case, the new era that we've entered beyond parameter efficient fine-tuning is using some of these massive models basically as is. And how we use them for different tasks is at inference time. And we actually provide the instructions typically via prompt. That is all the text to something family of models. And the core thing here is that it requires minimal training or no training at all. And you're already getting some state-of-the-art results in a variety of domains. So that's how we came to be from the dark ages to what we consider now foundation models. And next, I want to talk specifically about text-to-text foundation models. Here I'll be talking about PaLM, which is the family of models that Google uses and underpins Gemini and Gemma. I am not familiar with other models, but my understanding is that they are all based on the same technology. So for a text foundation model, what you have is a sequence of words, and then you have the actual model itself. This is during the learning time. And the idea is that you're going to have the previous n words, and you're going to ask the model to predict whatever the next word is. Now, something that is very interesting about this is that if you think about this, the way that training is being presented, we don't even need to have labeled data, right? We don't need to have your set of examples and targets. All we need here is just a large enough corpus of text. And what we do is we have this rolling window, and we have the n previous words, and we just say target is the next word, and then we keep rolling the window over and over. That allows us to have some pretty massive data sets with a very small amount of effort. I think that some of the bigger data sets that people talk about today is in the trillions of words, not technically words, but tokens. So that gives you a sense of the scale of the data that powers some of these models. So then you have, a sequence of words, and here I'm simplifying. Typically, it's a much larger context window, but let's say that you have the previous 3 words, and you try to predict what the next one is. And let's say it's going to be time. And you do this over and over, and every time you see a new word, you ask the model to predict it. And if it gets it right, it gets the weights get a little more solidified. If it gets it wrong, you compute whatever the loss was, and then you adjust the weights ever so slightly, and you do this over and over and over. But again, this is a rolling window. So here's the neat trick. Whatever was your previous output now becomes your input. And then you do it again over and over and over. So this is during the training time, but then the same happens during inference time. Once you've trained this model and you have, some kind of context, in this case, it could be your prompt, you're going to ask it to detect the next word. And then once it's produced that next word, you actually flip it around, and that becomes your input. And then you go on and on until you have a full sentence, a full paragraph, or even a full document. And this is why you see in many cases some of these models being used in a way that is almost streaming. You see the word typing one word at a time. Well, it's not that the model is actually typing. It is that it is predicting one word at a time, and it needs the previous sequence of words to predict the next word, including the word that it just predicted. So that is during the training and inference time, but let's just try to break it down into the different steps. First, we have the training process, and that is to predict the next most likely word. But let's think about what that looks like from the model side. If all I'm doing is predicting the next most likely word, that works in a very mechanical way. Let me give you an example. Say that I want to ask the model what the capital of France is. Well, the best way to prompt this model will be to say, the capital of France is, and then you point at the model and you fill the blank because it has been trained to predict what that next word is. but that's not how humans speak. That's very mechanical. So to bridge that gap, we actually go through a second phase post-training, and that's the fine-tuning phase. Sometimes it is called instruction tuning. And that's when we teach the model to respond in a Q&A fashion. So we can ask the model, what is the capital of France? And the model will actually respond to the question because it has been trained to detect what a question is and how it should answer. It is during this stage that we also typically do a lot of the safety tuning for the model and add a lot of the safety guardrails in terms of responsible AI. After the fine tuning is done, we basically freeze the weights, and now the weights are no longer going to be updated. Then we go into the inference phase. This is when you provide some kind of prompt to the model, and then the model is going to respond. And then between the inference phase and the output phase, this is actually a very active area of research. And this is when we're actually teaching models how to quote unquote think. And the idea is that you can do a whole lot of tricks during inference time to help models improve their performance by simply combining different steps when it comes to inference. For instance, rather than simply answering the question, you can tell the model and tell me step by step how you're going to reach the answer. That's called chain of thought reasoning, and it actually is proven to improve performance significantly. This is all done after training. You're simply asking the model to do things in very specific ways that happen to improve the performance, but the actual weights of the model are frozen in time. So that is for the foundation models and the text foundation models. Next, we are going to go into some of the meaty topics of this of today, which is, okay, so we have these models. How can we measure some of the biases in this model? And I guess I should have added some slides about this, but a bias is which way does the model tilt for some topic. It doesn't mean there's going to be something harmful, but at the very least, we're going to try to measure which way the model tilts for a specific question, topic, or query. So let's take a deeper look at the token sequence modeling. By that I mean, how can we predict, or how does the model predict that very next word? So you have your input. It's going to be a sequence of words. And now we're talking about specifically words. Then that's going to go through what is called the tokenizer. The tokenizer is essentially all we had earlier for the word2vec that we mentioned earlier. It's just tokenizing a word, a sequence of letters, into a sequence of numbers. So now we have a token or a collection of tokens from your input. The reason why this is many-to-many is because there's not an exact one-to-one mapping from word to token. But I don't want to get too deep into that. So for now, you can have a mental model of one word to one token. Is going to be just fine for the purpose of what we're going to discuss here today, but just know that that is not technically accurate. So you go from a sequence of words to a sequence of tokens, and then comes the prediction stage, and you go from your sequence of tokens to a new sequence of tokens. And that's again using that rolling window, and the input becomes the output, and so forth. And once you have your sequence of tokens, you detokenize it, and then you have back a sequence of words, and that is your output, and that is what you're going to see at the end. But let's zoom in a little bit on that very next token prediction. So when you do your next token prediction, there's a thing called sampling. And what is happening is that you have your input token, again, not technically accurate, you have a sequence of tokens, and then you have a sequence of, or a collection of probabilities for what the next most likely token is going to be. So if I say, for example, the cat is on the, and then the next word may be one of n, and let's say that the most probable one, the one here that is 0.45, is perhaps roof, okay? So that's just any word, but it could be on the bed, it could be on the street, it could be on many other things. All these different tokens represent all those quote unquote words, and some have a higher probability than others. And then we're going to pick one of them, and that's going to be our output token. Well, how many of these tokens we sample is called the top K. So if you ever see in the use of LLMs and some APIs, you may see a parameter called top K. This is what it means. This is how many of those tokens you are sampling. Then let's say that we pick the highest one. Well, that'll be some pretty, that'll be the greedy sampling method. But if this is a probability, it can actually be any other. We can actually get unlucky, roll the dice, and actually get somewhere that has a lower probability. How much variability we allow the model to choose when it comes to these probabilities is called the temperature. The higher the temperature, the more likely we are to pick a token with lesser probability. But this is all still in the random or pseudo-random domain. It's not going to be exact unless you have a temperature of 0, in which case you fall back to the greedy algorithm and you're only going to pick the most likely token. This is why when you have a temperature of 0, you have fully repeatable results, because you're always going to pick the token that had the highest probability, and that's not going to change. So let's just get into some interesting topics here. And please understand that this is all for illustration purposes. When it comes to responsible AI, we actually have to deal with some of these topics. I hope that I don't offend anybody here today. I like my job. Please don't make me lose my job. Don't take this out of context. So say that you have a prompt like, let's ask the LLM, who is better at driving, man or woman? And you ask the LLM, answer the question. Most likely, you're going to get, some form of politically correct statement because it has been trained safety tuned and say, I'm sorry, but I am a large language model, blah, 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 blah. And that's great and all, but we are here to measure bias. I actually want to know, does the model internally think, and I'm using the term think very loosely here, does it tilt more towards men or women to answer this question? So let's go back to our token sampling. I have, again, a sequence of tokens here, but I don't really care what the next most likely token is. The reason being is that the model has been trained to tell me something that is politically correct. I actually want to know, forgetting all of this typical sampling procedure, I want to create my own sampling procedure, and I want to look at only 2 tokens. I want to look at the token man, and I want to look at the token woman, and I'm going to look at the relative probabilities, and that's going to tell me what the model is tilting towards. Now, this has a lot of dangers, and we're going to discuss that in just a minute, but the core concept here is that I'm saying to the model, forget everything you know about how to predict the next word. I don't care about that. I just want to know, poke under the hood, and take a look at exactly within those specific tokens, which ones are the most likely. So let's do a little illustration here to better visualize what I'm talking about. So when the model is going to output something, it has the entire vocabulary, So we're not even doing the top K now. Let's just look at the entire vocabulary. For a model like Gemma, that's about 250,000 tokens that are possible for the next token. And their relative values are called the logits. And the logits are directly proportional to how likely it is that the next token is going to be picked, the one that has that value. And when it comes to measure the probabilities, again, I only want to look at a select few tokens. In the example I used earlier, it was 2. Here I'm highlighting 3 tokens. Let's say I want to look at just the probabilities of these 3 tokens that I shaded in blue. So I remove all the other logits, and now I have just the 3 logits left that I am interested in. In the next step, I'm actually going to convert them to probabilities. This is done with a thing called the softmax function. I don't want to get too mathy here, but it is just a very basic way of converting a sequence of values to a sequence of probabilities. So we have our target logits, then we use the softmax function, and we get back a collection of target probabilities. One interesting property that is very convenient here is that the sum of the target probabilities is equal to 1. So we can actually look at the relative weight of each of the probabilities, which is very convenient when we're trying to do something like measuring the bias of the model. So far so good. We have a number of target tokens, and then we convert those to probabilities. And this is what it looks in Keras. Again, I don't want to get too technical here, but I want to demonstrate that this is not all that complicated in terms of code. It's a handful of lines. This is how you create a layer that is going to give you the probability of a sequence of tokens that you have pre-selected. And then this is how you can define a model that uses that layer using Gemma as the base model for an example, and using the men and women examples for the two target tokens. But again, I don't want to spend too much time on this. Happy to answer any questions later about the code. But the main point I'm trying to make here is that it is relatively simple. So back to our example, if we ask the model, who is better at driving, men or women, we're actually not going to let it answer. We're simply going to poke under the hood before it can answer. We're actually going to look at just the two possible tokens that we're interested in, men or women. I said earlier that this is relatively dangerous, and the reason is we have to be very careful about what we're actually measuring. In this case, we want to measure the tilt between men and women, and that makes sense, and that is a valid research question. But you need to keep in mind that this is a general purpose methodology, and it can be misused, misconstrued, or straight up not make any sense. I could simply ask, okay, which one is the most likeliness token, aliens or Chihuahua? That is telling me nothing about the model bias or the relative probabilities. I mean, it's telling me, strictly speaking, the relative probabilities between the next word being either aliens or Chihuahua. But from a semantic standpoint and from a research standpoint, this answer is not going to give me anything revealing. So just like with many other topics of research, you have to think about your question beforehand and then test your hypothesis, as opposed to just going hunting for some valid results and then trying to figure out how to interpret them. That is one of the core dangers that you can, one of the core landmines that you may encounter using this technique. So that is for how to measure the token probabilities using the large language models, and I even showed the handful of lines of code that is required to do this with the Gemma family of open models. Next up, we're going to talk about a thing called counterfactual generation. This is a slight deviation of the topic, but it does make a lot of sense in the context of measuring biases.
Sorry, Oscar. I see you got a question from Aditya. But are you holding? I think we're holding. Are you holding questions until to the end, or are you happy to take questions now?
Let's make sure that we hold questions at the end. I want to make sure we go through the content, and I'll make sure that we have a few minutes left.
Cool. So if you could just hold your question.
Okay.
Hold that thought.
Yeah. Okay.
Okay. Thank you. So let's talk about counterfactual generation. So instead of talking about men versus women, let's not focus on a specific entity. Let's say men are good drivers, yes or no. And now we're going to measure the probability between yes and no. Okay, yes and no. And then something very interesting we can do is that we can swap men with women. And now we can measure whether the model now thinks yes or no are more or less likely when I swap men with women. But this is a general purpose methodology. I can actually swap this with any entity that I want. I can say Americans are good drivers, or I can say blank are good drivers. Think of some entity or ethnic subgroup or any other kind of social group, whatever you want. You can swap here, and then look at the relative probabilities. The first one is what is called the baseline, and all the others are your counterfactuals. It doesn't matter which one you pick as the baseline. The idea is that you need to have some kind of reference and comparison that you can then measure the others against. Using a more, let's say, interesting example, imagine that you have some job matching AI power application, and you have some resume as input, and your job is to match that resume to one of n possible job openings. Well, one way that you can measure how biased your model is that you can have your resume with some templating, like you blank out the name, and then you have your prompt that's going to evaluate whether a resume meets specific job qualifications. And then what you can do here is that you can change the name for one name of a specific subgroup. So you can swap the name for male names, you can use female names, you can use Hispanic names, You can use any other kind of subgroup name that you think may tilt the balance for your model. And this is a very good way for you to empirically measure whether your model is more or less biased. Technically speaking, your model should be absolutely not biased at all when it comes to the name, right? A name should not matter when it comes to job matching application. So this can be a very powerful tool that is using the same concept that we said before of measuring the next token probability. So that is for counterfactual generation. And the core thing is that you need to change one variable at a time. Otherwise, it is very difficult to draw the causal relationship between what you changed and the outcome. So we're going to shift gears now. We talked a lot about text-to-text models. We're going to talk about text-to-image foundation models. I'll explain how models like Imagen works, but this is how the whole family of the whole family of diffusion models work. So you have first an input image in combination with some kind of label. Think of it as a caption, something that describes the image. We have the portrait of a cat, and the text is cat portrait. And in the next step, we're going to add some noise to our input images. And we leave the text as is. And the goal that we have is for the model to remove the noise, to predict the denoise image. And we're going to do this many, many times with many different kinds of images, as diverse of a group of images as possible, with as many different captions as possible. And once we're done, we're going to have a very good image denoising machine learning model, AI model. And that's great, but that's not necessarily generative AI. But now we're going to play a really cool trick on the model, is that instead of having an image with noise, we're going to give the model simply noise. There is nothing else here. And then we're going to tell the model, here's my beautiful dog portrait. Can you please help me remove the noise in this image? And the model is going to tell you, well, I don't know about that, boss. Well, no, of course it's not. The model doesn't know what it's doing. It doesn't know that there's no dog here. The model is going to do what it's told, and it's going to dutifully tell you, here's your beautiful dog portrait. And that dark pixel over there, that must be the eye, and that part over here, that must be the ear. Here's your dog portrait. And you produce what now is a novel image. So this is how, in very hand-wavy terms and very much only scratching the surface, how diffusion models work. I think last time I gave this talk, somebody compared this to gaslighting the model. So that was a pretty funny analogy. You're fooling the model into thinking that there's some kind of image that needs to be denoised, and you give it that text, that caption, to give it a hint of what is lurking, quote unquote, lurking under the noise, and then you produce a completely novel image. This is why when you can have the same caption multiple times, you're going to have many different output images because you have very different underlying random noise. If you were to use the exact same random noise with the same parameters, you'll be getting the exact same image back because these things are, in theory, deterministic. So that's how these models work. Here's illustration from the Keras website. I don't know if the animation is working very well over the connection here, but you essentially see how a bunch of noise that is multicolor gets converted into flowers. And this is just purely from removing the noise in a sequence of steps until what you get closely resembles some made-up flower, but that's not a real flower. It's a completely random image. And each flower looks different because the underlying noise in each of the squares is simply different. So that is how diffusion models work. Now we're going to discover a couple of tricks for how we can measure the biases through a thing called latent space interpolation. So we're going to go back to latent space once again. How diffusion models work is that you first have your input text plus some noise. I'm not picturing the noise here. And then that input text gets converted into some embedding. Again, this is just a sequence of numbers. Then that embedding gets converted back into an output image. So you think back of the latent space image that I had earlier of the cube. The text goes into the cube as a sequence of numbers, and then you go back out of the cube, and instead of converting it back into text, you're converted back into some image. And this is great and all, and that means that similar texts are going to output similar images because they're just closer together in that latent space. But what we can do is a thing called interpolation. And the reason is we have a collection of numbers that are produced from a sequence or from an input text, but then we can do that for a different text. So we have another input text that is converted to a different embedding. When we're in latent space, this is just math. It is just two sequences of numbers. We can actually go and meet those two numbers together through a thing called interpolation. We're basically drawing a line in the n-dimensional space and sampling across that line. And here's the cool part. Because we are in latent space, we can actually draw images out of those intermediate steps. The thing that is a little difficult to grasp as a concept is that on one end we have an input text, on the other end we also have an input text. In between, there's no text. It is just something between those two concepts. So you may have two completely unrelated two completely unrelated words like dog and watermelon. And what is between dog and watermelon? We don't have the words to express that, but the model itself has some kind of mathematical representation, and at some point it's going to cross the threshold between dog and watermelon, and we don't know what's in between. But we can use this directionality between those two concepts to see which way is tilting. And we're going to see how to do that in just a second. But first, let's look at an actual example, once again, from the Keras website. And we can go from the first prompt being a watercolor painting of a golden retriever at the beach to a completely unrelated prompt, a still life DSLR photo of a bowl of fruit. And we can see how the model slowly goes from one to the other, going through many intermediate steps. In some of them make some sense to us as humans. In others, it's just how the model internally represents this conceptual reality. And we can see how it slowly but surely goes from one to the other. There's a few jumps here and there, but we are seeing in real time how the model represents these concepts in a very visual way, which to us humans is a very good way to understand how the model is biased. And we can, once again, bring it down to a more gnarly example in the world of responsible AI. So let's say that we have a first prompt, kids playing at the playground, rich neighborhood. And then we have a second prompt. We only change one word, similar to the counterfactual generation. Kids playing at the playground in a poor neighborhood. And what do you think is going to happen? Well, we are seeing, and I will not zoom into the picture too much to spare you the visuals of extra limbs and extra fingers. This is a relatively old version of text-to-image models. But we are seeing a very clear shift from lighter skin tones to darker skin tones. And I want to reiterate that here we are measuring bias, but we are making no claims at whether this is a harmful bias or not. We're actually measuring two things. Number one, there is a bias towards darker skin tones, but very importantly, we're establishing directionality. We're seeing that between the lighter skin and the darker skin, there's a darkening of the skin. So this helps us make a much stronger claim that there's a causal relationship between those two prompts and the direction in which that is headed, as opposed to having just two endpoints, and we can draw the correlation, but it is much harder for us to establish that causality. So that's how we are using the latent space and then the interpolation to measure the biases in models based on how those two concepts are being drawn from one to the next. And that's all I had today. I promised to leave time for questions at the end. I know we went a little bit fast, but I wanted to make sure that we got ample time to answer whatever questions you had. Thank you everyone for being here, and I'll take any questions now.
You've demonstrated some very powerful ways of measuring the bias. What do we actually do with these measurements of bias? How can we make changes or make improvements to the models after we find out that there are these biases?
That's a great question. So the first, when it comes to biases, there's typically two stages. You first have to measure the bias in hopefully the most empirical way possible. And then in the next stage is mitigation. The mitigation of biases is very much on a case-by-case basis. And you have to evaluate a whole lot of things that definitely cross into the ethical and philosophical line. It is a topic that gets significantly removed from engineering, at least at the conceptual stage. I don't work too much in that, at least I don't have that much experience in that, but I can tell you that it absolutely depends on the specific domain. For instance, in the example of counterfactuals, you can pick some things that are known to strictly not have any biases. In the case of resume matching, it's a good example. The name should not have any effect. But using the very same set of counterfactuals, it'll be totally okay for the model to understand that some names are associated with certain cultures or ethnicities. So you're talking about the exactly same bias. In one case, it is harmful. In another case, it is not harmful. So you need to mitigate those biases only for the harmful cases. And that's a whole lot of gray areas between what you should do and you shouldn't do. And there's a very nuanced amount, or it's a very large amount of nuance required to mitigate those biases in a way that you don't swing the pendulum too far in the other direction either. I know that was a very long, hand-wavy answer to your question, but it really just depends. The mitigation of biases totally depends on your use case and your domain.
I think Aditi was next.
I can go.
Please.
Yeah. So, Oscar, could be a dumb question, but so I try to search both answer. Who is driving better? Who is better at driving, men or women, on Perplexity as well as Gemini. So when I got a response from Perplexity, it says like clearly states like research indicates XYZ men are better or women are better because XYZ reasons. And then when I ask the same question to Gemini, uh, so it's like the response is different. It says it's not a simple question, it's a difficult question to answer, and gave reasons because number of miles increases, men are better, women are less. So there's not a definitive answer. So what is the decision making point, like an end user whom should we trust more, or is it like based on tokens they select or design they make? Why there is no firm answer? Like, is it based on models?
Okay, so that's a great question, and I'm afraid I won't have a good answer either. It totally depends on the specific model, and a lot of how these answers are formulated come from the safety tuning stage that I mentioned earlier. And different companies are going to safety tune their models in a completely different way, and that's going to depend on whatever AI principles they choose. I know at Google we have actually we're very transparent about which principles we use. I think the URL is ai.google/responsible or responsibility. I think also ai.google/principles works. And the idea is that we have a very clear definition of what we believe should be used when it comes to AI training. And that is what goes into our safety tuning stage. Another company, another organization like Perplexity are going to have a whole different set of principles, and they're going to have a whole different way of measuring and mitigating biases. And that's why you're going to see a very different response. Now, from one version of Gemini to the next, you may see a slightly different response, but very likely they're going to be on very similar lines. The reason being is that the principles have not changed. The underlying data may have changed a little bit, and the models may have improved a little bit, but you will not see a drastically different response because our principles have not drastically changed. So once again, the answer is it totally depends on the model and is going to be heavily affected by the safety tuning stage. And that's what's going to determine what that next collection of token sampling is going to happen. Now, if you have access to the model, like in the case of open models like Gemma or Llama, you'll actually be able to look under the hood and empirically measure what the model is actually thinking about when it comes to the next token. But for some of these API models, like Gemini or Perplexity, you're left with a black box, and whatever the model is giving you is whatever the parameters were based on temperature and the top K and so forth. So you're not able to actually measure the bias. You're left with just the black box, which includes the safety tuning that is mostly driving the response. Does that answer your question?
Yes, yeah. And it will, same as you said, for example, if in Perplexity I use a pro version where I can select the model, the answer might change, or based
Yeah,
on.
absolutely. Absolutely. It's totally going to depend on the model, and different models may have wildly different versions of safety tuning. So you can expect very different answers.
All right. Thank you so much.
I think Gisela was next.
Hi there, this is Gisela, PhD student at University of Melbourne. Thank you very much for your talk. It was very clear and very understandable. Thanks very much. I have a question regarding the way prompting the model or asking the model to find the bias. So I was thinking about do you, when you ask is women or are men better at driving, or are show me pictures of kids playing in a rich neighborhood, in a poor neighborhood. These are examples that we are coming up with, right? But don't you think that this is also introducing more bias into the process, because we are already biased, right? And coming up with this kind of example, like how can you, or I don't know if the question would be like, do you think it's possible to come up with examples, or to get an idea, and strategy on how to measure bias without putting our own bias into the model?
Okay, Gisela, that's a wonderful question. Very difficult to answer as well. It is true that we are very much introducing our own biases when we are choosing the questions, right? And maybe there are other biases that we should be measuring that we're not measuring, but we just didn't think about them. The key problem here is that what makes a bias harmful or not harmful is an entirely human decision. And that's why there needs to be a human that chooses which bias we are measuring, which biases we're mitigating, and how we're mitigating them. We absolutely run the risk of introducing our own biases. And this is why ensuring that the process is as diverse and inclusive as possible, to have as many viewpoints as possible, and taking into consideration as many different backgrounds as possible, is absolutely crucial to having truly responsible systems. Because if you leave this to just the one engineer that happens to have so and so background and happens to have so and so understanding of specific biases, you can absolutely do more harm than good. So this is very much a process that involves a very large, not very large, but a fair number of people, and it requires a very nuanced understanding and a very careful thinking of the topic. And the reason being is that this is entirely a human construct. It used to be a human question, but we better be careful about how we choose that question to avoid making things worse and introducing our own biases. Does that answer your question?
Thanks very much. Yeah, that's a very good answer. Thank you.
Pablo, and just remember, we only got 3 minutes, so be quick, Oscar.
Yeah, so thanks, Oscar. It was great talk. My question is very simple and more probably in the technical side of things, is where this bias correction lives. Is that more in the embedding space, in the mathematical token representation of the concepts, or the guardrails need to be added in the product that it produces? Is when we realize about that. It's more where I'm curious to know at what level that can be corrected.
Okay, great question. And once again, that's going to depend on the specific bias and the mitigation that we choose. The bias itself lives in the purely at the mathematical level. But once the model has been trained, it is very difficult for us to distinguish at what layer. If you have access to different checkpoints of the model, you can actually see at what point the bias was introduced, because you can do the same measurement at different checkpoints of the same model. In my experience, most of these mitigations are introduced in the safety tuning, but mitigations are not just done by introducing, but also by removing. You can actually look at the underlying data and look for specific components of the underlying data that are introducing those biases, and you can individually, filter them and remove them as needed. Does that make sense?
Yeah, thanks. Thank you.
Final question from Kunal.
Thank you so much. Oscar, really nice hearing to you again. Always insightful. My question goes, maybe it's a good point to end on, as models get more complex and we use it for more diverse applications. Like, for example, the current vision language action models like OpenVLA or RT2. How do we measure bias in that? Are there any new developments or techniques of measuring bias that we are looking forward to?
Okay, another great question. So today I focused on latent space representation, which requires to have direct access to the model. This is the most objective way of measuring bias that I've come across, and one of my personal favorites. But there are plenty of other ways to measuring bias from more black box perspective. They are not going to be as robust when it comes to establishing that causality, but it allows you to measure biases in a much wider range of models, including those that are not open models. So this is a very much active area of research. Anybody who tells you that they're an expert, they're probably lying, because we are all learning as we go. This stuff did not exist 5+ years ago. So I can keep that in mind, please, with all my answers. This is stuff that we are actively looking into, but make no mistake, we are all learning as we go.
Thank you so much.
And that's a great place to wrap, bang on time at 11. Thank you so much, Oscar. And just a reminder that Oscar will be doing another talk on the benefits of open models and research in February next year. Thank you, everyone, and have a great day. Cheers.